I think most of you know me already, but as Barbara said, my name is Jean-Marie van Rensburg. I've been with QFinSoft for a couple of years, and today I'm very happy to share with you the optiSLang webinar. So let me get my screen shared. Can you guys just give me a thumbs up if you can see?
Yeah,
yes, we can see. Thanks, Johnny.
Okay, wonderful. All right, so I'm going to jump in, and then as Barbara mentioned, we'll go through a couple of slides. Don't too much. It's not only slide-based. I do have a nice demonstration as well that I pre-recorded, and then we'll end off with some questions. All right, so I wanted to not only present you some slides today, so to make this also practical and relevant, I'll walk you through a real-world example. I can use optiSLang base with our flagship licenses. So just to take note, and as Barbara has also mentioned, very importantly that in our latest release, 2025 R2, we have the transition from DesignXplorer that we used previously to optiSLang base, which is included in your flagship licenses for mechanical, CFD, and for EMAG. So throughout this demonstration, we'll go all the way from the geometry to the simulation, all the way to the sensitivity and optimization within optiSLang. That's also done in Workbench, by the way. And then we'll end off with some more insight into the sustainability of our product and how we can reduce the material while keeping temperature within safe limits. Just a quick note, I'm not sure if some of you may have joined my colleague Aidan's webinar last week. It was on cloudburst, and he also used a heatsink example, but today's example is still a heatsink, but it is quite different because we'll be using optiSLang base within Workbench to do a full in-depth parametric study. Right, so let's get started. Okay, so before jumping into optiSLang and optimization, I just quickly want to talk about why this topic actually matters. So firstly, as you may already be aware, electronics are just getting smaller, more compact, and just getting hotter every day. And we don't always have the luxury of using big heat sinks in these kind of applications. Secondly, sustainability targets are being pushed for us to use less material while still maintaining the same performance or even better performance in some cases. So it's no longer just about does it work, it's also now about does it work efficiently, is it sustainable? Thirdly, doing this manually is definitely not scalable. So we can't keep on just guessing designs and running trial and error, especially when we have increasing complexity in designs and increasing number of parameters that play an important role. So we need these tools not to only simulate or to automate the simulations, but also to help us to automate these types of design decisions that we need to make. So finally, in thermal design, as you may also already know, is the typical challenge that we sit with is the trade-off between mass and temperature. So we want a lighter heat sink, but we don't want the electronics to overheat, for example. And this is where a multi-parameter optimization tool like optiSLang becomes very powerful. And it finds this sweet spot design for us automatically without us having to use that brute force of just try a couple of things until we get to the right answer. All right, now also before we can optimize anything, we first need to make the model parametric. And that means turning the key design inputs, and this can be anything from geometric parameters to some material properties or even some boundary conditions in your simulation. You can turn these into parameters and then they can be automatically varied by the software. So in our case today, we will have geometric parameters such as the fin heights, the fin thickness, and the base height, which I'll show you shortly as well. And you can also parameterize boundary conditions, as I've mentioned, in the simulation itself as more input parameters. So in this case, I also added a fourth parameter, and that is the emissivity on the surface of this heat sink, just to kind of investigate whether you can control the thermal performance better by not only reducing or playing around with the geometric parameters, but also looking at other ways to make your design more sustainable. Okay, and then on the right, we extract the outputs or our response parameters, which we usually have then objectives for, or constraints. So in this case, we have the mass and the maximum temperature as outputs, which we would like to parameterize for. And the problem is, though, if you have a design and you only have, let's say, 10 parameters, if each of these 10 parameters have 3 values, then you end up with something like 60,000 different combinations of these parameters. And this is something, again, that you can't just solve by using brute force. You need a tactical and a smart way to go through all of these kinds of different combinations and then see what works best. And that is exactly what optiSLang then does. Okay, so what exactly is Ansys optiSLang? It's basically just a framework for parametric design exploration and optimization for any number of parameters. So you'll see that there are some limitations on the optiSLang base that comes with your flagship license. But if you did have the full optiSLang suite, then you could have hundreds of parameters and you could run that and build your circuit models, and it will kind of compete the parameters off to each other to see which one plays the biggest role, etc. But that all comes with your optiSLang licenses that you can add. Okay, so essentially, in summary, optiSLang just helps us to automate the simulation workflows so that you don't have to do that manually, and then it also explores these design variations for us to find the best design. So just to position where optiSLang base then fits in, so on the left, you'll see optiSLang base, which is what we now have with our standard flagship license. So it is replacing DesignXplorer. It's basically working the exact same way, maybe not in the background. For the user interface, you won't see much difference. In the background, it's just using different algorithms to the previous DesignXplorer. So basically, it will allow you, as previously, to run parametric design studies, design of experiments, sensitivity, meta models, and some basic optimization. And this is all done directly within Workbench. Okay, then we have the Pro and the Premium versions of optiSLang that build on this. So Pro will give you a bit more access to more powerful algorithms for optimization and robust analysis. And it has more advanced meta modeling, like the adaptive meta model that is native to optiSLang, that is very useful. So unfortunately, we don't have access to that in the base license. Okay, then we have Premium. This lets you start integrating full workflows. You can link third-party tools, and you can then also automate these processes. And then we have Enterprise, which is basically for scaling, kind of employing optimization across big teams, linking it to something like model-based system engineering and HPC and cloud, etc. And then at the bottom, and this is also something that's relatively new, is the optional optiSLang AI Plus. And this just gives you access to more sophisticated AI and machine learning algorithms that you can use for optimization. Right, but you don't have to stress too much about all of this. Today's demonstration that I'll show you a bit later only uses optiSLang base. So everything that you'll see that we do, you have included in your flagship license. All right, so this is where the big shift then really happens. So then what's new and why should we care? Now, the key change is literally only that the optimization is done within your solvers via optiSLang instead of DesignXplorer as previously. And it is directly built into your solvers like Workbench. So literally the workflow will stay the same. It's just leveraging some different things in the background. Okay, so what can it do? You can parameterize anything up to 10 inputs. So you do have a limitation, unfortunately, on that. We can perform a standard design of experiment studies. We can do basic optimization and basic meta modeling. So it'll do anything that optiSLang does. It just has some restrictions on the type of algorithms and things that are available. Okay, and in terms of licensing, that is the best part. As I've now mentioned a couple of times, you don't need an add-on license or an extra increment. It is already included in your license, so no additional charge on that. Okay. All right, so now with DesignXplorer being phased out, just to quickly show you what exactly you do still have with optiSLang base. So everything that you see on the slide is basically included with your existing solver licenses. Okay, so you still have wizards to do your sensitivity and your simple optimization, but there are some restrictions to keep it lightweight. So you can still do a meta model of optimal prognosis, or a MOP as they call it. It just is only really, it still generates a response surface model for you, but it's only surrogate modeling. there's no full competition between the models as you would find with the full optiSLang license. Okay, then you still have access to the standard design of experiment methods like your classic Latin hypercube sampling methods, factorial, and some other random sampling methods. And then you're also left with some basic optimizers, which includes the evolutionary algorithm, which is the default that it uses. Okay, so in summary, or in short, it's basically the same workflow as DesignXplorer. We just have better technology under the hood, and it's fully integrated into Workbench. Okay, I guess that's kind of why Ansys is calling it the base, because it's a solid starting point for optimization within the solver. All right, then this very last informative slide, I would say, does reiterate a couple of things, but I wanted to just keep it in to make the full picture clear and keep it in one place. So it clearly shows you how optiSLang base fits in and how it compares to Pro, Premium, Enterprise, and AI+. So basically, you'll see your restrictions on your number of parameters, constraints, and objectives, some of your algorithms, and of course, yeah, you don't unfortunately have access to the advanced adaptive meter model, which is really cool. And then the bottom of the slide is also a concurrent solver variant licensing that you can also get with optiSLang Premium and Enterprise. That just allows you to run design points in parallel. So with one optiSLang license, the +3 and the +7 just indicates you can run +3 simulations at the same time using this one license. But in any case, to get to our demo overview for today, I'm just going to give you a quick overview on the slide, and then I'm going to jump straight into the video on the next slide. So basically, we start an Ansys discovery where we will create the heat sink geometry, and we will parameterize the fin thickness, the fin height, and the base height. And you'll see that these are being parameterized as sketch parameters. Just to note in advance, you can still parameterize existing designs already by using the pull or the move tool in discovery. Okay, then these parameters along with the geometry is then sent to Ansys Mechanical, where we will set up our steady-state thermal simulation as we normally would. And then in addition to the geometric parameters, I also added the fourth parameter of emissivity to see how that can control the thermal performance. And then our objective for optimization is clear. We want to minimize mass while still keeping the temperature below 85 degrees. All right, then what happens next is optiSLang will build a design of experiments and a meter model, and it will optimize then based on this meter model. But a very important last step is to take this final best design that it gives you and then sending it through the solver again just to validate whether your meter model is giving the correct output. So what this does, then it will change the geometry with that best design parameters, send it through the solver, and then give you a final validated design. Okay, and that's the loop. So from geometry to simulation, optimization to a final validated design. Okay, so the next slide, I'm going to be jumping into the demonstration. Okay. So we start in Ansys Workbench 2025 R2, very important. We pull in a steady state thermal, rename it, usually good practice just to keep up to date with what's happening. And then we will open a new discovery geometry. You can also do this in spacetime, by the way. Very importantly is then to activate the history tracking to ensure that you're capturing the history so that you can parameterize in the end. So you'll see I did speed this up a little bit. So I'm just drawing the fin cross section basically. And I'm starting off with just doing the drawing first and getting the cross section done. The next step is then to add your parameters dimensions. So this is just to keep track of what you're actually parameterizing in the end. And then after that, it's quite useful then to add fixed dimensions as well. Because remember, when you update these parameters, you have to ensure that your sketch is not going to break. So you have to include any dimensions that will stay constant. And in addition to that, the sketch constraints that I'm applying now is also super critical. So the equal distance and the equal length constraints work quite well to ensure that your sketch updates correctly when you update one of or two or all of the parameters. Okay, what's then nice to do is you can use this history tracking to test the parameters. So you just change it to some other values within your parameters range and kind of just click the play button to see that everything updates correctly. Okay, so if you're happy, all looks good, I like to just change it back to my initial values. Not that that's necessarily needed, but I like to do that. Next step is then to add the parameters. Very easy, just by clicking that little icon. And then also very importantly, you can rename them straight here in Discovery. This is also just to make it easier for you to reference them later on in your workflow, especially in the optiSLang workflows. All right. Then once you're done with that, we just need to extrude the face still to make the full geometry. So in this case, this is just a constant value, and you'll see that the extrusion or the pull operation is also recorded in your history tracking. All right, back to Workbench. As you know, usually just assign our material. In this case, I'm adding aluminium from the Granta material data simulation database. And you can see that it's into the project, and then we can edit mechanical. All right, in mechanical, literally just following your structure tree from top to bottom as usual. We'll assign our correct material to ensure the thermal characteristics are correct. Generate a very basic mesh. In this case, at least the geometry allows for a really nice swept hexahedral mesh. Very important to keep your meshing parameters the same throughout your parametric study so that it doesn't influence the results. All right, then your boundary conditions. In this case, I just have a simple heat inflow of about 4 watts on this face, which will also stay the same. Then I'll add 2 heat loss boundaries, convection, just for natural convection. So I'm applying that to all the other faces, and just adding a constant film coefficient. So this is also something you could parameterize, but we won't be doing that in this case. Also just adding a radiation boundary condition to the same faces, and in this case, the emissivity will be parameterized. Okay, then mechanical, checking your boundaries. You can add your result items before you solve, just to add the parameters. So in this case, to parameterize mechanical, you just click the little checkbox. So I'm currently parameterizing the maximum temperature, the mass of the geometry, and then also the emissivity I parameterize as an input. Okay, so input or output, you can do a mechanical. Then also just a good sanity check to see if your model actually runs and that it doesn't give any errors. Okay, then if you go to Workbench, you'll see that your parameter set is done as per usual. You have a list of your input and output parameters. Also good practice to rename them here as well, as you directly reference them in optiSLang a bit later. And that's about it. So when you run optiSLang later, you'll see your design points being listed here. Okay, this is where the fun starts. You'll see the optiSLang wizards there. We'll start by dropping a sensitivity wizard. The next, or the first step will always then be to define the ranges of your parameters. Now this can be influenced by other geometry around the heatsink, or I don't know, there's many different things that can influence this, but very important to put those ranges in so that optiSLang can select design points within those ranges. Next up is to define the optimization objective and constraints already in the sensitivity wizard. So you see we can minimize the mass. Then we can also just add a constraint to the temperature. Here you can see we're referencing the names that we gave it earlier. Very easy to input all of this into your wizard. Okay, you can see it's currently violating the constraint, but you don't need to stress. Then another thing that they do recommend you do, or that's good practice, is to ensure that your objective and constraints are in the same order of magnitude. So that's why I divide by 100. Right, then you'll select your sampling method. You'll see some of them are grayed out, and that's because of optiSLang base. And you can select an appropriate sampling method for your problem. And then you'll see your sensitivity wizard being created. From there, you'll simply click update. And now what it's doing is it will be populating the design point table with a bunch of different design combinations for parameters. Okay, so you'll see if you open your parameter set, all of your design points listed there. And then if you go into the sensitivity wizard itself, you can also see your design points up as well. All right. Then after the design points have been gathered, you can select your meter model that you want to build. So I'm just selecting a normal polynomial one. So basically, the optiSLang base will now just kind of build a surrogate model based on the results that you gave it so that we can do rapid optimization. All right, then if we view the results from Workbench, it will open the optiSLang post processor to show you everything. So firstly, you'll get a nice response surface showing the relationship between your outputs and inputs. It gives you a coefficient of prognosis where a value of 1 is really good. So 0.97 is really, really good as well. It shows the prediction isn't too bad. You can pull in your design parameter where it's selected a best design. This will change downstream with optimization. It's just an initial kind of guess, but you can already peruse that kind of information as well. Then most importantly, I think for the sensitivity analysis is to look at your total effects, because here we can see which parameters play the biggest role. You can see for the max temperature, the emissivity and the fin height play a major role, whereas for the mass, the fin thickness played the biggest role. So this is really insightful when you're trying to work with a large number of parameters. Okay, from there we can just drop our optimization wizard on our sensitivity results. Everything is basically preset for you. There's nothing you need to really fill in. Minimal inputs, we can update from there. So what it's doing now is it will run a bunch of design points using the mop solver. That's why it's so fast. And then from that, it will give you this best design. Okay, there's also some other post-processing plots that you can pull in, like an angel plot, things like that. But importantly, now that we have our best design, is to validate it. Again, minimal inputs that you need to put in. So we can quickly just update. You'll see that it runs through the geometry, updates the model and everything, and then we can look at our results. All right. So this can sometimes happen, as you can see here, when we ran our final design through the validated solver, our max temp constraint was violated. And this can sometimes happen if your meter model or your surrogate model is not maybe sensitive enough. So in this case, what I did is I just made the temperature constraint a bit more strict. I reduced it to 80 degrees. So unfortunately, you kind of have to run through this sensitivity wizard again, but it really doesn't take too long. Okay, so I literally just reduced that to 80, basically just rerunning the optimization wizard as well. And then ideally from here, then we'll see our new results. If we look at the sensitivity results, we should see the max temp be below 80 now. Small now, I didn't highlight it with the cursor, but you'll see it's about 79. So this looks good as well. Again, we can look at our design parameters that it's selected for our best design. Again, we can look at our total effects and everything else. Right, then the last step again is just to do the optimization on your map. Again, your ranges and your objectives and constraints are taken from your sensitivity, so nothing you need to fill in here. All right, then if we do our validated design, we'll just update the optimization quickly. Here we go. Okay, so it gives us some new design parameters in the end. Also shows you the history of the iterations, by the way. Okay, and then finally here, if we now run our validated design, just to reiterate, it's literally updating the geometry and doing a full solver run to validate that best design. And then from the results, we can then now see that the design parameters that we got now does not violate the constraints. Everything looks good, and we can plug those in the geometry and use that as our optimized model in the end. So that brings me to the end of this little video demonstration. I hope it was insightful for you. Just maybe to end off with a last slide, there are many resources available on Ansys optiSLang as well, especially with them moving over from DesignXplorer to Base now. So there's lots of info on the Ansys Learning Hub if you have a subscription. There's also some free courses on the innovation space, and there are some webinars on demand as well that you can request, and in the help file as well, there's many different tutorials and things like that.